In this video, we're going to look at different classes of events. So we have three different ones to look at. First off is mutually exclusive events. Second off is not mutually exclusive events. And finally, we'll have exhaustive events. So mutually exclusive events, these are if one happens, then the other cannot. So for example, in soccer, if you're taken down in the box and score a goal, you'll either get the goal or you'll have the penalty. You can't have both. They're mutually exclusive. Getting one prohibits you from getting the other. In cards, you can draw a red card or a black one. There's no way to draw a single card that is both colors. Again, saying of this is you can't have your cake and eat it. That's the idea, mutually exclusive events. The other category is not mutually exclusive. This means you can have both. So in the example above, I said soccer and penalties, but I chose this one because in basketball, if you're fouled while taking a shot and the shot goes in, you do get the points for the basket and you get the bonus foul. So you get an extra shot after that. So that's called an and one. So you can therefore have both and they're not mutually exclusive. In the cards example, you can draw a king and a red card at the same time. So the king of hearts is a red king and the king of diamonds is a red king. So you can have both. So they are not mutually exclusive. Having one means you can still have the second. Exhaustive events then. In coding is an example where you need to think exhaustively. So you'd have to account for all possibilities. Your code would have to be exhaustive. So if a person was playing a number guessing game, so just like a pick a number, they could guess higher than the number, they could guess lower than the number, or they could guess the correct number. All possibilities will be there. So if the number was 7, they could guess lower and you might prompt them to say it's higher than that. They could guess 13 and you might prompt them to say it's lower. They could guess 7 and you might tell them that they're correct. In thinking about this now as well, you could also have some user that might enter a letter and not a number. They could have some strange character in there. So you might need to, again, think about that and be exhaustive so you can think about all of the different things somebody can do and then have an option for that. If you're planning, a good plan should be exhaustive. So you need leave no stone unturned and you plan for every possibility or scenario. So there's the three different categories. Try and remember the titles at least: mutually exclusive, not mutually exclusive, and exhaustive. So we're going to look at these now in Venn diagrams. So Venn diagrams are a useful way to represent this, and a lot of the times in probabilities, how you look at the problem and how you go about solving it will dictate if it's going to be easy or not easy. So mutually exclusive events. Let's say you're in a match and you take a shot. The shot can either be on target or it can be wide. It can't be mutually exclusive. Statistics wise, if you hit the post in soccer, it's counted as not on target, so it goes in the wide category. So they're the two things you can have in a match. If you have 17 shots, if you have 4 of them on target, the other 13 have to be wide. There's none in the middle. So they're mutually exclusive events. One means you can't have the other. Then the mathematical rule for this: the probability of being in A plus the probability of being in B. That's the probability of A plus the probability of B. Again, until you see a tricky problem, it probably doesn't make that much sense. But the key thing in here is there's no overlap. There's no thing that's in both categories. If you have it on target, and you add up all of those and you add up the wides, so the probability of being this plus the probability of being that is equal to the probability of being either. So no overlap is the key one here. Now we'll move on to not mutually exclusive events. So in here I have the UFC champions at featherweight and lightweight. So these are the only 5 ever UFC featherweight champions: Jose Aldo, Conor McGregor, Max Holloway, and Alexander Volkanovski. My apologies, 4 champions. And then the lightweight champions, slightly older division: Jens Pulver, Sean Sherk, BJ Penn, Frankie Edgar, Ben Henderson, Anthony Pettis, Rafael Dos Anjos, Eddie Alvarez, Conor McGregor, and Khabib Nurmagomedov. So these are not mutually exclusive. Being champion of one means you could be champion of the other. In fact, Conor McGregor, as you see here in both lists, was both the champion at this weight and the champion at this weight. So our rule here is you would have to watch out for this. So again, I'm going to show this with an example and then I'll amend the notes. Here we have 1, 2, 3, 4 people. So if you're guessing randomly, you have 4 people that could be here. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people over here. So the probability of being A looks to be 4 out of 14, and the probability of being in B is 10 out of 14. But if you add those up, you can see that you have Conor McGregor in twice. So Conor McGregor should not be listed in both lists separately. He should be in the middle. And the reason I have him in both lists is to show this. It's necessary to subtract the intersection to avoid double counting. Because if you count Conor McGregor here and you count Conor McGregor here, you've counted them twice. So you want to avoid that double counting and you want to place in the middle. So if you look at this overall, so I'm going to edit this in a sec. So in looking back at this here, we have Conor McGregor crossed out of both lists but is in the middle. So we have 1, 2, 3, 4 people in this list. So the probability being A and 4. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people over in here. So the probability is 10. But if you add 4 plus 10, you get 14. And we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different people. So we have to subtract this intersection to get it to the proper number. This is what we call double counting. So if something is not mutually exclusive, then you can have them in both camps. So that's not mutually exclusive. So that's looking at that one there. And then following on underneath, we have exhaustive. So exhaustive is all cases. So a simple one. The weather is either sunny or it's not sunny. There's no other option it could be. In this case, we have the probability of A plus the probability of B equals 1. So all of the options have to add up to be 1. That's your certain probability. So that's exhaustive. That might be a little bit mutually exclusive as well, but this is your key thing here for the probability equals 1. I have an example here to finish with. So A and B are two events such that the probability of A is 8 out of 15 and the probability of B is 2/3. The probability of A intersection B is 1/3. First off, find A and B together. So if we look at this, in this left hand side circle here we have 8 out of 15. In this right hand circle here we have 2/3. So that's our A and our B on either side. However, 1/3 is in both, so this 1/3 is also accounted for. So if I want to find out the amount that's just in this section here, is the overall 8/15ths less this third, because that's already counted for. I don't write 8/15ths in here, or I go back to the double counting problem as I talked about it before. In this full circle on the right hand side, we have 2/3. 1/3 is in here, so obviously 1/3 has to be out here. So I have those crunched down here. A union B is this left circle here, which is 8/15ths without the middle bit. This just right hand circle here is 2/3 without that middle bit, and then I have to add back in this third in the middle. I could have just took that plus this plus that, but that's just the way I did it there. So overall, in this A union B, we have 13/15ths. That's less than 1, so that's possible. Next question we have is, are A and B mutually exclusive? Explain your answer. So again, always a good idea to get back to the theory. In the theory, we have the probability of A plus the probability of B equals the probability of A or B if they're mutually exclusive. So if we figure out these two sides, if they're equal, it is. If they're not, it's not. So the probability of A, that's being on the left-hand side, that's 8/15ths. The probability of B, that's on the right-hand side, that's 2/3. So the overall probability of this is 6/15ths. Then we have the second one, the probability of, so it's not 6/15ths, 6/5. I knew there was something wrong there. So the probability of being on either side is 6 out of 5. Now again, that doesn't make sense because you can't be more than 1. So that's something we'll look at later on. So the probability of being then in A or B, that's the one that we worked out here. So that is 13 out of 15. So 6 out of 5 is not equal to, and again another typo, 13 out of 15. So they are not the same, so they are not mutually exclusive. So that's using our rule and applying that. So that is the technical way to do it. There's a couple of other ways as well. Just from the Venn diagram, we can see that there is an intersection. There is something in that middle section, that third. So that third being in the middle tells us that they're not mutually exclusive because obviously it's in both circles. Another also, so also, the probability of A plus B is greater than 1. The only way that can happen is if you double count. So the fact that that's greater than 1 also shows it's not mutually exclusive. But this way up here is the better way to do it. This way is fine. This way won't always be a giveaway, because sometimes you could have something that would be outside the circle, so out in the universe. So maybe that's what I should have included up here in this exhaustive thing. So you could have sunny, cloudy, and then wet outside. So you'd have your whole universe would be exhaustive. But that's the idea overall. You got your three cases: mutually exclusive, can't be in both; not mutually exclusive, can be; and exhaustive means it covers everything.